So, hey everyone, my name is Amrik, and today I'm going to give a talk on how to think like a browser, where we discover what happens between the time you visit a URL and get first and largest paint on the screen. So, a little bit about myself. I work as a web performance consultant and developer at Yottaa, where I consult and help major e-commerce brands fix their performance issues. I spend most of my time in dev tools, chasing down LCP, INP, and bad third-party scripts. So before we get started, here we have three different frames. The first one is blank at 0 milliseconds. And then you see the second frame, which rendered something on the page at 324 milliseconds. We name this as FCP, the first contentful paint. And at 758 milliseconds, we see more things on the screen. We call this the largest contentful paint. But what happened between these time frames? What was the browser busy doing? That's what we're going to uncover next. So before we even start talking about rendering, we need to talk about the race before the race. This is where the browser has to find the site's address, open a connection, and agree on encryption. Even before rendering start, network and server latency can eat up 100 to 200 milliseconds just setting up the connection. Once the connection is established, browser sends a request to get the HTML document from the server. The browser needs to wait for the server to send back the first byte. This is where TTFB is calculated. When the browser gets the first byte, it can begin parsing and rendering. But here's the good news. If you visited the site before, or if the site is well optimized, the entire phase can be skipped or drastically shortened. Modern browsers, we use TCP and TLS connection using HTTP2 multiplexing or connection pooling, and the browser can cache DNS lookups, sometimes for minutes or even hours. So if you revisit a site, the lookup phase is skipped entirely. And if you use a service worker, then the HTML itself can be served from local cache, bypassing the network entirely. Even without a service worker, the HTTP cache can serve assets instantly if cache headers allow it. So as soon as the first chunk of HTML arrives, a little state machine starts turning it into the DOM. As it starts, at the same time, a side thread called preload scanner guesses which resources like images, CSS, and fonts you'll need and starts grabbing them from the markup. But if the the main parser hits a plain script tag with no async or defer attribute, it pauses the parsing until that script finishes parsing and executing. And if that script comes after a style sheet, it also has to wait for CSS to finish loading first. So the main parser builds the DOM step by step as HTML streams in, but it pauses if it hits a blocking script without async or defer or a style sheet, because those can affect what comes next or block scripts that rely on CSS. At the same time, the speculative parser runs ahead and starts fetching resources like images, CSS, and scripts early, even before the main parser reaches them. It prioritizes anything marked with preload or sent via early hints, so key resources load early. So the structure alone isn't enough. The browser also needs style. As the HTML is parsed, the browser builds the DOM tree, a structured representation of elements like div, paragraph tags, and other tags. At the same time, every link, style sheet, or style block gets fetched and parsed into CSS object model. This defines the computed styles like colors, fonts, margins, position, etc. But here's the key. Rendering cannot begin until both the DOM and CSS object model are ready. So even if the HTML arrives quickly, if your critical styles are buried in a 200 kilobyte CSS file at the end of the head, the painting will stall. The parser waits for the CSS and scripts that depend on layout, like the ones that read offset height or modify styles, they're also blocked. Once both the DOM and CSS object model are built, the browser merges them into a third structure, the rendered tree. This rendered tree filters out elements with display none, script tags, meta tags, etc., and only elements that are visually renderable and styled make it into this tree. So after the DOM and CSS object model are built, the browser merges them into a render tree, but not everything makes it in. Like we just talked about, only elements that are actually visible and have computed styles. So stuff like script tags or anything with display none gets skipped completely. This is the tree the browser uses to figure out what to draw and how it should look. Font, sizes, colors, positions. The DOM gives structure, the CSS object model gives styling, and the render tree brings them together into real renderable boxes on the screen. So once the render tree is ready, the browser runs layout, also known as reflow. This is where it figures out the exact size and position of every visible element. It walks top down from root element and assigns pixel values for width, heights, margins, and positions based on the box model and computed styles. This is a performance sensitive step because layout must be completed before pixels can be painted, and layout can become very expensive if it's triggered repeatedly. So when does a layout get triggered? When you change styles, for example, element.style.width equals 100 pixels. When DOM changes affects geometry, adding and removing elements, or when you read layout related properties in JavaScript like offset height, get bounding, client rag, scroll top. These forces the browser to flush the layout pipeline synchronously, blocking the main thread to give you accurate values. If you interleave layout reads and writes, you'll hit layout thrashing. Modern browsers are smart about performance. When you make a change to the DOM, like adding or removing a class, the browser doesn't immediately recalculate everything. Instead, it marks that element and some of its ancestor as dirty, meaning they need layout or style updates later. It batches those updates to do them all at once just before the next paint or when it absolutely has to. But if you ask the browser for a layout value too soon, like calling offset width, it's forced to stop and do all that pending calculation right then. So it can give you the correct value that interrupts the batching and can trigger a bunch of layout work in the middle of your JavaScript. When a lot of elements are dirty, that layout work can take time and turn into a long task, which shows up in DevTools and hurt your INP score. So once layout is done, the browser starts painting. This means it goes through each box and draws the actual pixels, backgrounds, borders, text, shadows, and all that stuff. It's basically turning the boxes into visuals. Some styles are heavier to paint than others. Things like big drop shadows, gradients, or overlapping elements can slow this part down. That's what you're seeing in this green chunk chart, time spent just drawing pixels. Some elements, like the ones with transform or video, get their own layers that moves them off the main thread so the GPU can animate them independently at 60 FPS. So all this run on the UI thread. Inside each render process, Chrome spins up one render process per side. Firefox and Safari stay a single process, but still funnel parsing, layout, and paint through a single event loop. Network, GPU, and storage live on separate threads or processes. So the critical rendering path, all this stuff we just talked about, is what makes up the critical rendering path, which is the chain of steps the browser must complete before it can paint anything on the screen. Parsing HTML, building the DOM and CSS object model, creating the render tree, running layout, and finally painting pixels on the screen. These steps happen mostly on the main thread, so any blocking resources like a large CSS file or synchronous JavaScript can halt progress completely. It's called critical because each step depends on the previous one. The browser cannot style without CSS object model, and it cannot layout without the render tree, and can't paint pixels without layout. If you block the parser early, you delay everything downstream. That's why performance isn't just about how big your assets are, but where and how they're loaded. The goal is to keep this path short and non-blocking. Inline only what's needed for above the fold content, preload your LCP assets, defer non-essential scripts, and avoid layout trashing. If you speed up this change, you don't just improve metrics, you make your site feel faster. So in this slide, we have some milestones that matter to capture these metrics. First contentful paint and largest contentful paint are two of the most important milestones in the rendering path because they reflect what the user actually sees, not just what the browser is doing. FCP is when something first appears on the screen, typically a text or logo. LCP is when the most meaningful visual, often a hero image, our main headline is fully rendered. These aren't just technical milestones, they're perception metrics. They tell us how fast the site feels. Users don't care about parsing when the parsing starts, they care when the page looks usable. A 500 millisecond shift in LCP can mean the difference between the site feeling snappy or sluggish. What's powerful is that LCP is directly influenced how well you optimize the critical rendering path. Same for FCP. If you inline above the fold CSS, preload this LCP image, defer blocking scripts, or reduce layout shifts, you'll see LCP improve. These are metrics that reward doing the right things for users, not just scoring well in lab. So in this next slide, I want to show a quick demo of before and after for same site, where on the left side, we have a slow version where FCP is rendered at 1.3 second time frame. So what is causing the delay on the left side? It's that CSS is blocking the render. A synchronous script pauses the parser, and the LCP image is also loaded late. Now on the right side, we see the same page, but it's fixed. The CSS, the critical CSS is preloaded and the rest is deferred. JS is also deferred, so the parser never stops. And the LCP image is preloaded, so it paints early. Just by removing these blocker from the critical path, we cut the FCP from 1.3 seconds to about 600 milliseconds, which is a 50% gain. And that could mean your users might not bounce if they land from an external ad or social media sites, because if they see something render 50% faster, they have higher chance of staying on that page and interacting with it. So how do we actually speed things up? There are 4 high impact levers that help the browser reach first paint faster. Just pre-connect and preload, get ahead of the parser, warm up DNS and TCP early, or preload key assets like fonts and LCP image before the HTML even asks for them. One caution here is you should not preload and pre-connect all your resources, because if you pre-connect and preload everything, then nothing's preloaded. So only preload out of the fold critical assets that you really need. And async and defer JS prevent scripts from blocking the HTML parser. Let rendering keep going while JS loads in the background. All the unnecessary scripts are scripts that are not needed until the DOM is ready. They all should be deferred or at least loaded asynchronously. Deliver the styles needed for the above the fold content right inside the HTML, so there's no delay waiting on CSS files. You should inline the critical CSS that's needed for above the fold content and delay or defer the rest of the CSS that's not needed for above the fold content to make the browser paint pixels faster. Your LCP image or your LCP assets are also something that needs to be compressed or optimized. They should use good compression, right formats to reduce the decode and byte transfer time. All of these reduce friction in the critical rendering path. Less waiting means earlier paint. The goal is to remove friction from the browser before the first paint happens. So to wrap things up, I have created a mental cheat sheet where it's a simple framework. It's called Reduce. The goal is to reduce the amount of work browser is doing before it can paint anything on the screen and make the first paint as fast as possible. So it stands for reduce resource count, cut the scripts, fonts, and third-party tags that you don't need for above the fold content. Preload the hero image or fonts before they're discovered. So E stands for early handling the critical assets. D for deferring non-blocking work. Use defer async and lazy loading so parsing isn't interrupted. And U is for unblocking render critical CSS. Inline the styles that matter upfront and delay the rest. C is to contain layout shift, wrap dynamic parts in layout containers to keep layout local. And E is to eliminate heavy paints, avoid big shadows, gradients, and slow image decoding. If you can pull even one or two of these levers on a project, you'll make real measurable improvements on your metrics. So thank you so much for listening. I know it was a short talk, but I hope this helped you see how browsers work and made you see browsers less like a black box and more like a busy system with real choke points that we can control. If you want to go deeper into web performance or just know about dev tools, feel free to reach out to me. I'm always happy to chat.